to determine the maximum current, or load, that can be drawn from a 415 volts to 230 volts three-phase, three-wire transformer, particularly in marine applications, follow these steps. Firstly, determine the power rating of the transformer. The power rating is typically indicated on the transformer's nameplate. This rating is expressed in kilovolt amperes, or kVA. Secondly, calculate the primary voltage. For a 415 volts to 230 volts transformer, the primary voltage is 415 volts. Thirdly, calculate the primary current. Using the power rating and the primary voltage, you can calculate the primary current, denoted as I sub P, using the formula I sub P equals P divided by the square root of 3 multiplied by V sub P, where P is the transformer power rating in kVA and V sub P is the primary voltage in volts, which is 415 volts in this case. Fourthly, calculate the secondary current. The secondary current, denoted as I sub S, is equal to the primary current multiplied by the turns ratio of the transformer. For a 415 volts divided by 230 volts transformer, the turns ratio is approximately 1.8. Therefore, I sub S equals I sub P multiplied by 1.8. Fifthly, calculate the maximum load current. The maximum load current is the secondary current, I sub S. This is the maximum current that can be drawn from the transformer at the rated voltage and frequency. As an example, let's say the transformer has a power rating of 10 kVA. Using the formula, I sub P equals 10 kVA divided by the square root of 3 multiplied by 415 volts, which equals approximately 13.91 amps. Therefore, I sub S equals 13.91 amps multiplied by 1.8, which equals approximately 25.4 amps. Therefore, the maximum load current that can be drawn from the transformer is approximately 25.4 amps. In review, firstly, identify the transformer's kVA rating from its nameplate. Secondly, note the primary voltage, which in this instance is 415 volts. Thirdly, calculate the primary current using the formula I sub P equals P divided by the square root of 3 multiplied by V sub P. Fourthly, determine the secondary current by multiplying the primary current by the turns ratio, about 1.8 for a 415 volts to 230 volts transformer. Fifthly, the maximum load current is equivalent to the calculated secondary current. Let's walk through the calculations again with a 20 kVA transformer to illustrate the process further. Firstly, the transformer rating P is 20 kVA. Secondly, the primary voltage V sub P is 415 volts. Thirdly, we determine the primary current I sub P. Using the formula I sub P equals P divided by the square root of 3 multiplied by V sub P, we substitute the values I sub P equals 20 kVA divided by the square root of 3 multiplied by 415 volts. This calculation results in approximately 27.82 amps. Fourthly, to find the secondary current I sub S, we multiply the primary current by the turns ratio. Given a turns ratio of approximately 1.8, I sub S equals 27.82 amps multiplied by 1.8, which gives us approximately 50.8 amps. Fifthly, the maximum load current that can be drawn from this 20 kVA transformer is therefore approximately 50.8 amps. To enhance the explanation, let's consider a different example with a transformer rated at 5 kVA. Firstly, we identify the transformer's kVA rating P as 5 kVA. Secondly, we note the primary voltage V sub P is 415 volts. Thirdly, we calculate the primary current I sub P using the formula I sub P equals P divided by the square root of 3 multiplied by V sub P. Substituting the values, we have I sub P equals 5 kVA divided by the square root of 3 multiplied by 415 volts. This results in approximately 6.95 amps. Fourthly, we calculate the secondary current I sub S by multiplying the primary current by the turns ratio. With a turns ratio of approximately 1.8, I sub S equals 6.95 amps multiplied by 1.8, resulting in approximately 12.51 amps. Fifthly, the maximum load current for this 5 kVA transformer is approximately 12.51 amps. This method applies universally to different kVA ratings, allowing the adjustment of calculations as needed. Remember that these calculations assume ideal conditions. In real-world scenarios, factors such as transformer efficiency, power factor of the load, and ambient temperature can influence the actual maximum load current. Transformer efficiency refers to how well the transformer converts electrical power from the primary side to the secondary side. A transformer is never 100% efficient, meaning that some power is always lost in the form of heat due to factors like coal losses and copper losses. Typical transformer efficiencies range from about 95% to 98% for larger transformers, but can be lower for smaller units. The power factor of the load affects the amount of real power that the transformer can deliver. Real power, measured in kilowatts, is the power actually used by the load to perform work. Apparent power, measured in kVA, is the total power supplied by the transformer, including both real power and reactive power. The power factor is the ratio of real power to apparent power. A lower power factor means that the transformer needs to supply more apparent power to deliver the same amount of real power. This can increase the current flowing through the transformer windings and lead to overheating. Typical power factors for electrical loads range from about 0.8 to 0.95. Ambient temperature affects the transformer's ability to dissipate heat. Transformers generate heat due to coal losses and copper losses. If the ambient temperature is too high, the transformer may not be able to dissipate heat effectively, which can lead to overheating and reduce lifespan. Transformers are typically designed to operate at ambient temperatures up to about 40 degrees Celsius. If the ambient temperature is higher than this, the transformer's load capacity may need to be reduced. To account for these factors, it is best practice to consult the transformer's datasheet and direct the maximum load current accordingly. Dirting involves reducing the maximum allowable load current to ensure that the transformer operates within its safe operating limits. For example, if the transformer's datasheet specifies a maximum ambient temperature of 40 degrees Celsius and the actual ambient temperature is 50 degrees Celsius, you may need to direct the maximum load current by a certain percentage. Similarly, if the load has a low power factor, you may need to direct the maximum load current to avoid overloading the transformer. Always refer to the manufacturer's specifications and guidelines for directing the transformer under specific operating conditions. Keep in mind that these calculations provide a theoretical maximum. Practical considerations may further limit the actual current you can safely draw. These include voltage drop in the wiring, the ampacity of the wiring and connected devices, and adherence to electrical codes and standards. Voltage drop refers to the decrease in voltage that occurs as current flows through a conductor. The amount of voltage drop depends on the length and gauge of the conductor, as well as the amount of current flowing through it. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The ampacity of wiring and connected devices refers to the maximum amount of current that they can safely carry. Exceeding the ampacity of a conductor or device can cause it to overheat and potentially start a fire. Electrical codes and standards, such as the National Electrical Code, or NEC, provide guidelines for the safe installation and operation of electrical equipment. These codes and standards specify requirements for wiring, overcurrent protection, grounding, and other aspects of electrical systems. When determining the maximum load current for a transformer, it's important to consider these practical limitations and ensure that all components of the electrical system are properly sized and installed in accordance with applicable codes and standards. In summary, to find the maximum current you can draw from a 415 volts to 230 volts three-phase transformer, you firstly need to determine the transformer's kVA rating. Secondly, ascertain the primary voltage. Thirdly, calculate the primary current. Fourthly, calculate the secondary current using the turns ratio. Fifthly, recognize the secondary current as the theoretical maximum load current. Sixthly, adjust this value by considering factors such as transformer efficiency, load power factor, and ambient temperature. using the transformer's datasheet. Seventhly, always comply with electrical codes and standards for safe installation and operation. In marine applications, special considerations may apply due to the unique environment. Saltwater, vibration, and confined spaces can all impact the performance and safety of electrical equipment. For example, saltwater is highly corrosive and can damage electrical components if they are not properly protected. Vibration can loosen connections and cause equipment to fail. Confined spaces can make it difficult to access and maintain electrical equipment. Therefore, it's important to select electrical equipment that is specifically designed for marine applications and to follow all applicable marine electrical codes and standards. Marine electrical codes and standards such as those published by the American Bureau of Shipping, or ALPS, and the International Electrotechnical Commission, or IC, provide specific requirements for the design, installation, and operation of electrical systems on ships and other marine vessels. These codes and standards address issues such as grounding, bonding, overcurrent protection, wiring methods, and equipment selection. When working with electrical systems in marine applications, it's essential to be familiar with these codes and standards and to follow them carefully. In addition to following marine electrical codes and standards, it's also important to implement proper maintenance and inspection procedures to ensure the continued safe operation of electrical equipment. Regular inspections can help to identify potential problems before they lead to failures. Maintenance procedures should include cleaning, lubricating, and tightening connections, as well as testing and calibrating equipment. By following these guidelines, you can ensure the safe and reliable operation of electrical systems in marine applications. Always consult with a qualified electrical engineer or technician for specific guidance on your particular application. They can help you to select the right equipment, design the electrical system, and ensure that it is installed and operated safely and in compliance with all applicable codes and standards. Remember, working with electricity can be dangerous, and it's important to take all necessary precautions to protect yourself and others from electrical shock and other hazards. This information is intended for educational purposes only and should not be considered a substitute for professional electrical engineering advice. Always consult with a qualified professional before working on any electrical system. The steps we have reviewed are crucial for understanding the limitations and capabilities of your transformer, contributing to both the longevity of the equipment and the safety of the electrical system. For any further steps, consult a professional to fully analyze your specific situation to meet the requirements.